Okay, good afternoon. How you guys doing? Doing all right? Dressed up for something? What do you have going on? Okay, gotcha. Is it with people like from companies or is it? Oh, probably a good idea then. at least not a bad idea, right? Cool. Okay, so last time we left off talking about this problem, and I figured one thing I could do with you is just go ahead and put it in Excel, walk you through how I would approach solving this problem, make a couple notes. We already talked a little bit about what it would look like to address the chemistry in the problem or to neglect it. And it's really, we can take either approach. We've been talking about kinetics and then about how to derive some kinetic parameter, a rate constant, from a set of data. And so that's really the theme here. And this problem introduces something we haven't directly talked about yet, but it's a very common topic within water treatment, specifically disinfection. And that is this Chick-Watson kinetics. And I'm doubting myself here because I thought I had set the default to... Let me just take a quick look through my slides to make sure that this is the right slide deck or that the updates came through. Yeah, okay. I generally change the default pen color, so it's... Anyway, so the Chick-Watson kinetics here, it's a concept that says if we are degrading some organism, we can describe the rate constant as, or the rate equation, as a first order equation with respect to the amount of pathogen that's there, assuming that the other reactant, which is, let's say, chlorine or whatever disinfectant we're using, remains constant. And that turns out to be a pretty good assumption under most conditions. And so in this scenario, we would say the rate at which, we'll call it n for the pathogen, changes would be a negative K times a chlorine concentration, or disinfectant. So I'll say C disinfectant, times n to the 1 power, where n is the thing, the microorganism that we're changing, and C is a disinfection or disinfectant parameter. So the Chick-Watson model then says we're pretty much at a first order scenario when this is held constant. So within the context of a disinfection chamber, that's often going to be true, or we're often going to be aiming to achieve that. Maybe something like ozone that decays a bit faster, perhaps we are bubbling it and injecting it into the chamber throughout the system to maintain a relatively constant value of it. At any rate, that means that we can put K times this C for the disinfectant, both as a constant and just simply call it K star, and then it looks very much like any of the other stuff we've encountered. So under that circumstance, we could do our first order kinetic analysis, and in a batch system, we would know that we'll get dn dt, and we do the integration, so this would be negative K star times n, ultimately achieving natural log of n over n naught equal to negative K star t. So everything we've already seen that. The caveat would be if we wanted to solve for C, I don't know how much of the chemistry we'll get into. I'll probably give you a bit of a refresher when we get to disinfection. But the concentration for HOCl is going to be a potential equilibrium problem where we have to solve for, okay, at pH 6 that was given, what percent of our total chlorine is in this HOCl form. It turns out the pKa, again, we'll give you that reminder of what all that means if you don't remember, is about 7.5 for free chlorine, and therefore at pH 6, we're an order and a half magnitude away from that. So we're probably expecting 98% or so of the chlorine to be in the HOCl form. So this would be something like 98% of total chlorine. The problem itself is not even specific or explicit enough with the information, the task at hand, so I'm not going to bother too much. But if it had said we applied 2 milligrams per liter of free chlorine and HOCl has such and such a value and we're at this temperature and all that, then we clearly know, hey, we've got to solve for this to count how much is in the HOCl form. Anyway, we'll come back to that later when we talk more about disinfection. For the moment, I'm just going to bring up Excel and just put in these numbers for you and walk you through that process of linearizing it. Okay, so let's just go ahead and set up a couple columns. So we'll do time in seconds and PFU here. Okay, so we've got our data here, and we could actually go ahead and plot that if we wanted to, and that would be like we did in class, like I asked you to do, which essentially looked something like, if this was time and this was n, it kind of looked a little bit like this, right? Probably first order, but we weren't quite sure if we didn't measure anything. So what we can do to check to see if this is first order is to try linearizing it by taking the log. You can even do this with a log base 10, but I like to use natural log of n over n naught, and then plot that to see if that is linear. Then we're good. We can take that first order, take the slope of that, the line of best fit there, and get a first order rate constant. So to do that, I'll take the natural log of n, whatever current value at the current moment, divided by n naught. I'm going to go ahead and put the dollar signs that freezes the cell. Quick way to do that, in case you're interested, is F4. You can cycle through the different dollar sign configurations by pressing F4. So a little cheat code. All right, then I can fill that equation down. That will lock the n initial to the 0, the n at time 0, and then it'll give us at each point the value we have there. Okay, so that should look something like that. Now, once we have that, we can then go and add in a scatter plot. Add in the data. Okay, so we've got the data. Chart's a little messy, but we're going to ignore that for the moment. If we want to put this at time, and we could add in the other elements and everything. But for the moment, we can take a look, and it looks fairly linear to me. So we're going to go ahead and add a trend line. The R squared value will be a good addition in terms of how linear is this, or how good of a fit is it, so that can help us with that. And in this case, I'm going to go ahead and set the intercept to 0 because we really have to start through 0 anytime we have natural log of something over itself. That's the natural log of 1. Natural log of 1 is always 0. So it doesn't really make sense to have any kinetic parameter under normal circumstances start anywhere else. Now, sometimes you might have a time delay before the first order kinetics begin. That's actually occurs sometimes with disinfection if the bacteria have some cell membrane that's resisting perhaps chlorination for some time or some other attack. Maybe you have some amount of time before we start inactivating at a first order or the process begins. But we've got viruses here, and I don't see anything that would tell me we should shift this anywhere. So given that, I'm going to set that intercept to 0. Okay. All right, and then I also want to display the data here. Okay, so our regression here, we have r squared of 0.998, pretty good. And we have a slope value there that we can use as our slope for the kinetic parameter. So that slope then, we could say that's our k star. So k star would be 0.3758. And that's from our line of best fit. Okay. Good with that? All right, so from there we could then calculate k. K would be 0.3758 divided by our 1.8 milligrams per liter. And by the way, this 0.3758, we plotted that as a function of time, so our units have to be per second there because we were in seconds. So that would mean we have our answer being this 0.3758 divided by 1.8, and the units should be liters per milligram second. But this is a strange one because this is including the chlorine, right? You notice our K star is a per time. That's our combined constants giving us this per time unit. Whereas if we specify we're using chlorine to disinfect poliovirus, that will be a special distinct K star, or excuse me, K, for a chlorine paired with poliovirus. It would be different if it was ozone. It would be different if it was adenovirus. This is specific to that pairing, right? So we might even say this is K for HOCl to polio, if we wanted to really be specific and say this is that particular rate constant. Okay, we'll come back, talk a little more about that when we get to disinfection stuff. So my point here is we can take the data and extract the kinetic parameter, all right? And we can see a lot of different pieces that can go into that. We can see a lot of different pieces where that might come from. And I'm sure you've done things like this in the past, so hopefully we're all good on that. Okay. So then, last time we derived some equations. We got to a bit of calculus, and I said, we'll just take a look at this table later. Here's this table. And I've got it in a few forms here, the book does rather. It's quite convenient. So let's take a look at the pieces that we've already looked at, the 0 and first order reactions specifically. So as we discussed, the 0 order we derive from this expression where the rate of change is dc dt is negative k, this is a decay reaction, times c to the 0 power, right? And that just goes to 1. Whereas our first order, c to the 1 power, second order, c to the 2nd power. Okay, so we see each of those pieces as expected. Now, the integral then would look like, for the 0 order, the integral of dc from c naught to c would probably be the best way to write that, is equal to negative k for the 0 order equation, integrating from 0 to time t, something like that. So if we did that with those boundary conditions, we would get c at some time t minus c initial equals negative k times time. Now, this is a form where we put it in terms of a linear amount of time. So on the left side, this column right here, it has the book has solved this in terms of a time value where it's the t is not in some sort of exponent or in some weird spot, right? So we have essentially in I guess in a linearized time fashion. Whereas over here on the right, and for the zero order, it doesn't really matter, we have essentially solved for c. So c at some time t is equal to, that's this column. Okay, so for a zero order, we could say c at some time t minus ca is equal to negative kt. Could rearrange that to solve for c. It's very obvious. C equals c naught minus kt. Okay. First order, then this is our natural log system, and here's where we can keep it with a natural log to get our linear form, where we might plot it versus time and have something linear, a linear relationship to time. That's quite convenient, and that's probably a better way to write it, linear relationship to time. So on the left side, this left column, these are the linearized forms of our kinetics. So we can plot a line and get a nice rate constant with that line of best fit approach. So here's exactly what we just did with the ln of c over c naught equals negative kt. Can extract that k. And here they're labeling the k with a subscript to say, okay, this is the zero order rate constant. Here's the first order, second order, and so on. And of course, with the first order, we could also write that as c equals c naught times e to the minus kt. Okay, that's just the written right here. They put exp there for the exponent. Okay, that brings us to the second order. So the second order equation, if we take and derive, take the integral of dc over c squared equals negative k times integral of dt, the solution here is that we get 1 over c minus 1 over c naught. That's what I alluded to last time with low confidence. And so that would be, the linear form would be 1 over concentration minus 1 over the initial concentration is equal to k times time. Now, when we put that in, when we solve that for c directly, that becomes this equation here, 1 over c naught plus kt, and all that, the inverse of all that. So all that to the negative 1 power. So that's the calculus that we could go and look up in a book and remember, okay, that's the answer. Perhaps you already remembered that. Now we can actually do the same process for any value of n. And here's where it's a little more complicated, which is why we really like to have the book solving it for us. But what we're looking at is anytime we have an n for this rate order that is not known or simply not an integer, what do? We can't use one of these specific ones. And so we have an equation then that works for anything except a first order. And if it's a first order, then we're fine because we know how to deal with it. Okay, so we have this equation here where we would put in the c to the n power and try to integrate dc over c to the n power. Turns out we can, in fact, do that. It will look like this. And here's why the n minus 1 as a denominator means we can't have n equal 1. But like I said, we can go back to first order if that was the case. So here's an expression that should be linear with respect to time that gives us a way to linearize a rate that, or a reaction that's happening with an arbitrary rate order. So if 1.5, if n equals 1.5, we should be able to plot that on this and figure out, oh, hey, this is what's happening. And so we're going to take we're going to dive a little deeper into that and see how that might plot out graphically. The last part of over here would be the CT. We could rearrange that equation and solve for C. So we can use it, and we can solve problems if needed with a non-integer rate order. Okay, does that make sense? You on board with me to skip the calculus to get there? Sound good? All right. So when we are looking at data, our first question is probably, what's the reaction order? And in fact, if you've been involved with research, there's a reasonable chance that you've either been tasked with finding a reaction order, if you've done any sort of a chemical or biological or some reaction that you're trying to model kinetically, trying to understand it. Well, one of the first steps is to simply figure out, is this in fact, let's imagine you're expecting first order, is it in fact a first order reaction? Or maybe you don't know what's going on. What reaction order best fits this so we can best model it? Okay, so we have a few, we've already talked about this a little bit, but that idea to linearize it in terms of a linear dependence on time is very convenient. So a k times t gives us the k as a slope, and it's essentially becoming y equals mx, where x is time, possibly with a plus b, right? So y might be complicated, might be all this stuff over here, but at least on the other side, assuming we were able to handle y and plug in some numbers, then we can plot this as a function of k times time and get our kinetics. So 0th order, we do c versus t. First order, we do the natural log of c versus time. Second order, we do 1 over c versus time. And nth order, that's where we do the special stuff. We do this stuff versus time, okay? But that falls apart if it happens to be n equals 1, in which case we go back to this. Okay, so as you can see, there's a few things here, in order to determine which one to use, are we going to have to guess? One thing you could do, if you have the data, maybe you can guess, maybe you can plot it in each different way. Maybe we can take, this here, and instead of just taking, let me move this a little bit. Maybe we could also do just simply the PFU versus time, 0 order. We could do 1 over n versus time, and here we would just say equals 1 divided by that, and make a plot of that and check to see if that's linear. Even just at a glance, we can see, okay, we go from 1 to 3 to 8 to 14 to 33. That's not very linear. Just looking at, just chopping off a few digits here, but just looking at those numbers, you can kind of tell that's increasing. The time is linear. Those answers are not linear, right? So this would essentially be not the right way. Okay, so guessing kind of maybe works sometimes, but ultimately it would be nice to have some other tools. Okay, so let's take a look at some random data. And I say random, I think it is quite random. Looks like I took it from a book at some point and I forgot where it's coming from. So I've forgotten what this data is. So why don't you take a look and sketch it out and see what you can make of it. I'll go ahead and put it in Excel while you make a little sketch, or make your own sketches. I figured it would be a little more fun, so I did. It's not that I came completely unprepared on this one, because I looked at it and I was like, oh yeah, I don't remember where that comes from. That's perfect. We'll do it on the fly. What do you think? Got an answer? Some of you almost there. This one you can almost just eyeball it in terms of checking for a linear change, but the time is actually doubling every step you take there, so it's not quite as intuitive. You know, if it was 0, 50, 100, 150, 200, 250, and so on, that would be different. But since the time is going 0, 50, 100, 200, and then 300, that's not a linear increase per step you take, so it's a little off. All right. Yeah.
Is this supposed to step on the origin to know which order exists, or we just need to observe the trend?
What was the question?
Should it start from the origin? Like, should you observe the slope of the origin, or you should just observe the trend?
Yeah. Okay. So for this problem, or for the data that we have, the origin is not part of the data set in any piece of it. Now, usually when we take the natural log, usually I do natural log of C over C naught. They're actually just plotting the natural log of C here in this scenario. So the natural log of this nitride or NO2, I don't know if it's gas or liquid phase. So if it was C over C naught, we would expect it to go through the origin for a first order system. But otherwise, you know, none of these, the way they did it, I don't expect through the origin necessarily. But if you stop and think about that, kind of that predicament, if you might call it that, of, you know, normally we've been doing the natural log of C over C naught equals negative KT. Well, you could also simply write this as natural log of C equals negative KT plus natural log of C naught. So you have a y equals mx plus b in that sense. So even though that's not the way I would normally do it, it's not actually a problem to do it that way. And that would be for this guy. Okay. So which one is it? Which model fits it best? 0, first, or second order? Or none of the above? Okay, I see some first, and what else? Anybody? Okay, let's just take a look at my data and see if I did something funny, because I think it looks like second might be the best. Okay, so I put in the data here, just the way it was given. Since they gave us as a time versus C, a time versus natural log of C, and then 1 over C, I just kept it and plotted each like that. So my plot for concentration versus time definitely looks like it's not 0 order. And then my plot, where'd it go? Hey, hang on. I think I hit my keypad button and it deleted this one. Okay. Then we have the natural log of C here. Oops. It looks reasonably linear, and I bet if we did a best fit through that, it probably would not be too bad. Get an R squared of 0.98. So seems like I'm not too far from agreement for most of you looking at that. But at a glance, I actually thought that the other one? There it is. That the second order looked pretty good. So let's see what that tells me. That one says the R squared is 1, so I mean I don't believe that it's exactly 1 unless the data is just completely rigged. But I think I'm gonna vote for second order myself. Okay, is that whole process feeling all right? Okay, and I totally get why first order looked good. Okay, so just for the sake of the notes, this one kind of looked something like this. This guy looked fairly linear. Let me get back to where. But maybe slightly curved. And this guy looked something like that. Okay. And you'll notice when we do, if we go back to these equations, you'll see that when we do the derivation for a second order decay, on the right here, it is a positive relationship with time. It's just how it ends up plotting out, whereas the other ones feel a little more intuitively natural that for a decay experiment they're negative. It's just the way the math ends up working out. So it's not a surprise that it's increasing, just perhaps not intuitive. And again, what we're plotting here is 1 over something, which does invert it. So another reason why that it does make some sense there. But just noting that at a glance at it, we might think to ourselves, oh, it's a growth reaction, but you have to slow down and think about the units there, or think about the linearization process that we took to it. Okay, anybody recognize this little photo? Okay, one person old enough or willing enough. Okay, so this is just an old video game called Half-Life. So I want to talk about Half-Life. This symbol lambda is often used in radiation and as a term for half-life sometimes. Okay, so we can take data in the form of a half-life to figure out what our kinetics are. So I already mentioned this, but depending on our rate order, and sometimes maybe we can learn about the rate order from a half-life as well. So this becomes quite useful in certain circumstances where maybe it's not convenient to take a lot of measurements. Maybe we just know something about, it was decaying and suddenly we realized, okay, that's half. We are now at half or something. Half-life can be quite useful. So we're going to define this as the time it takes for a decay reaction until C reaches half of C initial. Okay, so that's pretty straightforward. That's just self-explanatory. So C at some time t, where t is half-life, t1 half, is equal to 1/2 of C naught, or C initial. Now, keep in mind, we don't have to have exactly time 0. If we wanted to, we could do an experiment for 10 days, and we realized, oh shoot, I missed day 0. I forgot to take my data point. Well, good thing we have several days of data. We could start at day 5 and watch until it halves from that as a starting point. And that can still give us a time with which it took to get to half. Okay, so take a quick example and go ahead and solve this for yourself. For a 0-order decay of 100 milligrams per liter of some species A, if our K is 3.75 milligrams per liter per hour. Calculate the half-life. some answers. I haven't gotten the numeric answer just yet myself. I'm just checking that like you have answers, feeling okay about it. Did you get both of them for A and B here? Okay, so we'll go through it with you. So for the zero order, what we'll find is it depends on how much we start with, which makes a lot of sense if we stop and think about a zero order equation. We're taking a discrete amount over time, no matter how much is there. If you are trying to, I don't know, build a mountain shovel by shovel, it's going to take a long time before you've done half of it, right? So it depends on how much you're starting with. Let's say you're removing a mountain with a shovel. That'll take a while. Whereas if you're doing an anthill, maybe one shovelful, right? It'll take 1 minute at most. So our equation for a zero order solved for concentration is C equals C naught minus KT. And again, the assumption here is we're just looking at batch scenarios. We're not doing any reactor kind of stuff at the moment, just looking at the reaction in isolation. So we were told we started with 100 and we're going to 50. So C at the half-life time should be 50. But, you know, so that, we can go ahead and write that as 50 equals 100 minus KT. So essentially we end up getting KT equal to 50. We'd take 50 divided by 3.75, and that would, you know, and we can probably best leave in the units here. So this will be 3.75 milligrams per liter per hour and 50 milligrams per liter. So that should give us some number of hours. 50 divided by almost 4, 13 point, yeah, exactly what we got. So 13 point, what was it, 33? Okay, hours. Okay, so good there. For the half-life of the first order one, as we will find, it doesn't really depend on what we started with, because when we solve this, we would say we're not given any initial concentration, but we do know that C over C naught has to be 1 over 2 as a ratio. So when we go ahead and divide both sides by C naught, that's what we get, and we'll say 1 over 2 equals negative e to the negative KT, or we can just say the natural log of 1/2 is equal to negative KT. And given that K, time, the half-life would be what? 2.24 hours, right? Okay, great. So just a little example there. Now, hopefully you can be comfortable if you were given the concentrations, or even just given the half-life for a first order, you know, oh, well, I can find the K from there. So you can go either way with it. It's convenient. You can do the same thing with a second order, given the right parameters. So I'd like to take that and kind of bring that to where the book is talking to us a little bit about it, saying, okay, for a given reaction order, we can solve for the half-life in this manner. So like we just did, first order, or excuse me, zero order, the condition is half of what we started with is equal to KT. That's literally where we got to just by saying, okay, we start with C equals C naught minus KT, subtract C naught from both sides, but one is half of the other, so we end up getting just half of C initial as our starting condition, or as our ending condition, is equal to K times T 1/2. Natural log for the first order is equal to negative K, natural log of 0.5 is equal to negative KT. And for the second order, if we were to have done that same exercise, you would find, because we could start with this equation and say, okay, well, if C at some time is half of this, that would be like saying, I guess, 1 over 1 minus 1 over 2, or yeah, that would work, is equal to kt. So it ends up being the same thing as saying 1 over c initial is equal to k times t. And then we could solve from there. Now, what's interesting is we can do this for any n. And just like what we saw for solving for the time, or solving for the linear form of it earlier, assuming it's not a first order, in which case we just go back up to there, then we have this equation that we could handle, and we could do the same process to get it in terms of the half-life. Okay, so if we know the half-life of something, but we don't know the reaction order, we still have something we could work with, okay? And we could put that in. And it turns out that one thing we can do, if we look at the complex equation here, we can take all of this, which again, I didn't bother trying to derive with you, all of that part in this equation and call that k star. Because what's in there is 2 to the n minus 1 power, so that's just 2 to something about the reaction order, divided by the rate constant that we're dealing with. Okay, so sorry, 2 to the n minus 1 minus 1. All that divided by k that we're interested in times n minus 1. All of that in there has information about the reaction order and the kinetic parameter that we're after. That's all that's in there. So we can call that just C star for the moment. Say, okay, here's C star, and then the portion that contains our initial concentration, C naught, that's to the 1 minus n power. Given that all of this is in a log, we can take this and say that's going to be equal to log of k star plus the log of the Ca to the 1 minus n power. But because it's a log, we can take that 1 minus n and bring it out front. So we just derive this 3-27 from this equation by calling this k star, as we like to do. Simplify things a bit, pull out the exponent in the logarithm, and we have this equation. So that actually becomes rather convenient, assuming that later we can go back and exchange from k star to this kn and deal with that. But even if we don't know the reaction order, we can know the half-life, or given a half-life, find the k. So that's pretty handy. Again, only if n is not equal to 1, but if n is equal to 1, then essentially our k star becomes ln of 2 divided by k, and we can deal with it there. So all this to say, we can actually test what reaction order do we have by plotting the log of our half-life, log of the half-life time, versus the log of c. And that you'll see that because this equation was in log of the half-life on the left. So that's our y value. And the x, this is our y here. And our x would be essentially 1 minus n is kind of like, if we're solving for the reaction order, it would be like that's our m. So m, and we're plotting this as a log of concentration plot, log of initial concentration plot. So this would be like b plus mx. Okay, so putting all this together just to show you that if we have some data, and maybe we take multiple half-life data points, in a first order scenario, half-life is always the same. It doesn't matter how much we have. But in a non-first order, anything else, the half-life will change depending on how much we start with. Okay, there is some dependence on how much is there. Are you taking it away in an accelerating manner or a decelerating manner, or is it just taking forever because you're doing one shovel at a time for a mountain, right? So unless it's the first order, in which case it's simple, then it depends to some extent on what we start with. So if we plot it this way, given the math here, we can actually find that slope as 1 minus n, and therefore find n. Okay, so that's the cool thing. And again, it doesn't necessarily have to be literally time 0, assuming we have plenty of data showing us how much time did it take to go in half at different points. You could also imagine all of this is for the value half, 1/2. You could potentially do quarter life, all right? You could do, 2/3 of life. The math would change a little bit, but the math could handle it, right? You could analyze it in that system. I don't recommend trying that. Maybe if you have a first order, it's nice and simple. You can just say, okay, natural log of 0.75 instead of 1/2. Sure. But in general, it's just convenient to do half-life, and all of this math is set up for that. Okay, so what we can do then with all of that is plot the log of our half-life, so log of the t1/2 versus log of c. And on that plot, we would see that for any value of n, we can get some result. Now, the one case where the log of our half-life, so our half-life, does not depend on our initial concentration, that's n equals 1. That's our first order, right? So n equals 1, meaning it's a first order reaction. Any other scenario, we can find our reaction order by taking the slope is 1 minus n, and so for any slope that we find, making this plot, we can say our order, we can solve for our order given that slope. So if the slope is, let's say, negative 0.7 over 1, then 1 minus that is an n value of 1.7. Have to subtract the negative there. Or if you're rising 1 for every 0.6 you're going, as in this case, then our n comes out to be 0.4. Somewhere between a 0 order and a first order. Okay? All right, so really all of this is giving you or showing you that there are tools, if you need to do kinetic analysis, to handle any sort of system. Okay, that's kind of the point. For the most part, we'll deal with discrete integers, but I'd like you to know that these options exist and kind of what we could do with them if we wanted to do something with them. So this is maybe a good example of something I might, maybe I wouldn't ask you an entire calculation problem on an exam, unless I give you a take-home exam or something. I'm not planning to. But I might ask you to interpret something, right? Give you the plot, put a couple of these lines on here with the slopes labeled and say, hey, what's the reaction order for each of these? Something like that would be in the realm of a question I might ask. Okay. Yeah.
So, I'm trying to imagine how, if you're doing this experiment, how would you come up with multiple half-lives? Data points that is multiple half-lives.
Yeah.
Just start with different initial concentration and then map out the half-lives of these different initial concentrations rather than multiple half-lives.
Yeah, it's a good question. I think you could. It would make sense if I took. If I took a set of data for you, and you plot a lot of data. So let's take this out a little further. Maybe if it'll let me grab that. All right, whatever. And we continued writing data here, right? So if I continue that data down, well, if you look at how long it takes for this to go into half, from 0 to 2 seconds, we already halved it. Now, this happens to be first order, so I know it's going to be about the same half-life every time. So every time we step down, it's approximately half. So you can actually, even from this data, we could guess this might be something like 140, and then 70, and then 30, maybe. You know, I'm doing not quite half, but somewhere close to half, 15, and so on. And so we now have, you know, 8 points where we calculated a half-life. And this third time we calculated it, C naught was 1200. And the C final was 710. So we can actually take a data set where we're just watching it over time, maybe for a long time, and then extract from there how long did it take to get us half starting from here. And then later we have a different starting condition, how long did it take? You could do entirely separate experiments and simply stop them when you reach half, start with 10 grams, and then start with 100 grams, and then whatever, some concentration or some mass. You could design that in several ways, but you can also take the same data set and extract it in multiple places. But that's a good question, because that kind of shows you how would you build a data set of log of C naught, right? You'd have to start it in each spot and then take the observation of how long did it take to get your half-life, and then do the log transform of that. Yeah.
What is a half-life useful? Do you have anything like first order?
Well, if you want to know the order of it, seems like that could be useful. I don't think it's very useful, practically speaking, for like zero order. I don't know if it's used much in second order. We just don't. I mean, second order equations are just a little funny anyway. They tend to be really quick reactions, so I don't know that we really use it a lot anywhere else other than first order equations. But perhaps this is one spot to figure out the reaction order as a way to analyze the data. Anything else? Any other questions? Okay. All right, so let's take a look at this example from our book. We have the following data collected from a batch system. Reaction goes from A to some product P, was proceeding, and we have time from 0 to 20 minutes, and some initial concentrations provided there and also plotted. So the question here is asking A, assuming that the rate expression, common rate expression here, R equals Kc to the n power, find the value of n. And then what is the reaction rate constant? And finally, what concentration of A will be present in solution after 60 minutes? So why don't we give that a shot? We have all this now. We have a little data set. You've already been using your calculators and such. We can kind of see it's not zero order, but maybe it's first order, maybe it's second order. Maybe the book is being mean to us and making us use that formula we just looked at. But I would start by checking the first and second order first. I should have the... So I think what I'm going to do is give you 5 to 7 minutes and then look through, let's see. Okay, then work through it with you. Okay, yeah, it's got the data analyzed for us. So let's give that a few minutes, see what it looks like. guess since I'm not over here yapping, people are ready to come in. Yeah, if you guys were taking an exam or something, right? All right. Well, I guess we should conclude, though, in the next couple minutes. How do you feel about it? Need some more time if you're going to properly solve it? Probably. Okay, if you just take a look at the data itself, anything that strike out to you? Notice anything interesting? I was just myself doing this because I haven't looked at the problem in a while. But if you take a look from 0 to 2 minutes, it's a little slightly more than half that's reduced, or slightly less than half that's reduced. And then the next 2 minutes, again, slightly less than half. So it kind of looks like, at least at first, the half-life is a little over 2 minutes. But then if I look towards later, let's see, I guess 8 to 10 minutes. Okay, probably the half-life is shifting a little bit, if I had to guess. So I'm not confident about that. That's just like, without looking at too much further, just eyeballing it. Doesn't look first order, or 0 order, and maybe not first order, excuse me. Okay, so we have a table for this, the transformed different ways. So we have, again, these times from 0 to 12 minutes. I guess they didn't go out to 20 minutes, but we'll just go with this. We have the log of the concentration. We have a column for time. We have a column for the half-life and a column for the log of the half-life. So they are going all the way to try to assemble that plot of, well, first I guess they're checking the log of C versus the time. To check that, so that does not quite look first order. Did you guys check 1 over C versus time? How does that look? Is that linear? No. What does it look like? So something like that, maybe? Okay. All right. So then we've got to find the n, right? So that means then we do need that log of the half-life, we'll say t1/2, equals k star plus 1 minus n times log of c naught, right? That's kind of what we have to do. Now, one thing I'll note here is that we actually don't even need to know anything about k star at this point, right? Early on, we don't need anything to do with that, because all we need to do is find the slope on this plot, log of t versus log of c naught, and then we know the order. Then we can go back and plug in, okay, k star was whatever this nonsense was, right? This guy. So once we know n, we can put that in, put our known n, and solve for the k with that. But that would take a little more analysis. We're out of time. Any questions on this before we go? Okay, but you see the direction we're heading, probably. Okay, we may look more at that next time, and just get to some other examples as well. All right, have a good weekend.